Hello, and welcome to another episode of Quarks and Quarter Notes. Today we're talking with Dr. Trey Holik. He has a doctorate in physics and is currently a professor at Angelo State University. He's an expert in electromagnetism and has worked in the cutting edge of that field. We talk about his work and schooling history, as well as some speculation on metaphysics and overarching questions in physics, as well as some more specific sharpening of our general physics understanding and electromagnetism.
So I guess we could start by just asking you, well, just how did you get into physics?
Sure. So in high school, enjoyed math, enjoyed science. I was quasi good at it. We went to a small school, so I wasn't really good at it, quote unquote good. I was good for 10 students. My high school class consisted of 11, so I had 10, rounding to 10. So out of that 10, I was okay. And then came to Angelo State and realized, oh, wow, I am behind.
Yeah.
Because, I mean, my first class as undergraduate was Cal 1 and Physics 1. I didn't have any dual credit anything. I didn't even have pre-Cal in high school. I just knew barely what a sine and a cosine is, some trig. And then what is a derivative? Oh, it's slope. So that was me. I was like surprised to me to understand that a derivative is slope. So starting from there, my first semester in college, but then I also had my first physics class. And what got me to major in physics from the get-go was a scholarship. I was offered to major in physics. I had a pretty high ACT score, which put me on their radar for a scholarship. And so that's what, oh yeah, you'll give me $500 for the semester or something like that. Yeah, I'll declare physics as my major. Why not? And then I was hooked. That's what it got me. That was the bait. And then the hook was actually whenever we were first talking about angular momentum in physics 1, and you bring out this lazy Susan or this frictionless rotating table and the bicycle wheel that rotates. And you see gyroscopic motion. And then you can take this bicycle wheel, stand on the frictionless table and rotate this bicycle wheel. And rather than the bicycle wheel just rotating, you start rotating on this frictionless table. Blew my mind. It seemed, I remember that same feeling. And I always want to my lectures and classroom to give you that same feeling of, wow, this is amazing. This is very cool. This is, how can that happen? And then moreover, not just how can that happen, but there's a very simple mathematical formula that governs this rotational motion. And we call it something succinct and simple called conservation of angular momentum. It seemed magical. And so, bam, I knew I had to know all there is to know about this weird subject called physics. And I mean, I slowed down. And there were some moments where like, wow, I just want to eat this stuff up. But ever since then, which that was in 2002, and here we are, 2022. So this is my 20-year physics anniversary, actually.
Dang, that's kind of cool.
This fall will be my 20-year physics anniversary. And then, of course, as an undergraduate, you taking these classes, keep eating it up, and it still is a satisfying course.
So what kind of expectations did you have of physics, and how do they contrast to what physics actually turned out to be in your mind?
No, I came in with zero expectation. Just I was not the kind of student that meditated on, kind of like y'all two, or maybe not y'all two, but I know that you, Tyler, I don't know you as well, John, but you tend to think after a physics class to think of all the manifold magnifications or implications and what does that mean about this or that. And I didn't think that in depth. I just saw something that is cool. This equation tells you how it works. And a lot of it was intuitive to me. So momentum. I didn't know that there was a formula for momentum until I took physics 1, but then it's like, of course, whenever two things collide, the heavier thing makes the other thing go backwards, but I didn't know how to solve something in that circumstance. But then conservation of momentum came up and conservation of energy came up. Oh, this is cool. And then that stopped. There was no discussion of, okay, well, does conservation energy applied to the macroscopic scale of planets moving or of galaxies colliding or the smallest scale, conservation energy of an atom. Like, but these are the big physics principles that apply at the big and the small. But I didn't think that way yet. So my expectation was low. And matter of fact, it was helpful because every path along the way in physics, there's a new application of conservation of energy. And then I'm thinking, oh, wow, I can understand this. Oh, wow, energy is conserved in the atom. So it made it a perpetual, oh, wow moment. I could talk more about that as well. But your question is expectation. And I came in not having any. Now, I double majored in math and physics, and the goal there is that math should prepare you better for physics, but at the same time math is a satisfying major in its own right.
So yeah, there's overlap there, but they diverge quite quickly, right? The work, or in terms of your major, or did you find they always
say converge?
Oh, okay.
Yeah, because the higher and higher you get in these math classes, you might say, oh, shit, topology, what? Or these weird algebraic groups, or how does that have physics application? Well, it does in string theory. So the highest levels of math and the highest levels of physics still they come back together. Matter of fact, I don't remember the name of it. There's a really interesting theory or idea, not theory, because you can't necessarily prove this, that every mathematical equation has a physical equivalent. You take any third order differential equation that's coupled to some other fourth order differential equation. Well, there is a legitimate physical system that is governed by this differential equation or series of differential equations. And this is where math guys over the last 300 or 400 years, because math is a lot more developed, right? The idea of physics and the idea of modern physics is very young, 100 years old, whereas math, the logic behind numbers and how they manipulate and compare is a lot older. But so many beautiful solutions to differential equations were simply just written out. This is a differential equation. I do no rhyme or reason to it. This has some sines and cosines, something oscillatory, something that's pushing on a thing. And I say pushing on a thing because that's the analog. I mean, physics, but the mathematicians just say, I'm going to take a single derivative, then I'm going to take a second derivative, and then I'm going to take an oscillatory term times the same function and set it equal to some other oscillatory form. What is the solution to that differential equation? I don't have it. No, is there a physical analog to it? No, it's just a differential equation.
Right.
But, and then the solution to this thing, they give it names, which is Legendre. This guy came up with solutions to several different differential equations, or Laguerre or Hermite. And so these are the names of certain solutions to differential equations that after the fact, physicists have come up. I mean, so physicists, we measure some things, and then, mathematicians already solved this differential equation.
Right.
Yeah, hey, we're done. Then I'm not saying a singular case. This happens a lot.
Right.
I can give you 4 examples off the cuff of my.
So maybe it's more like a couple trains that are going like parallel, and sometimes they go apart, but a lot of times they're crossing over and stealing from each other. And
that's a fine analogy, stealing from each other. No, that's actually important because now we measure weird things and then we don't know how to solve this weird circumstance. So we pitch it over to mathematicians who say, hey, we've got a rubric for dealing with that. Here's our rubric. And sometimes the physicists say, I think I can do better. Most of the times not, though. Usually when mathematicians come up with a slick way of dealing with some sort of logical puzzle or grouping things together, they're really good. I mean,
so did that double major work out that way in your like personal experience as far as?
Yeah, the thing about undergraduate level math and physics though is you're still building yourself a base. There's not any cutting edge. There's not any holistic, or there's not really any broad or cutting edge investigation of what the current technology, current knowledge base is. So the undergraduate degree in both physics and math, well, that prepared me well to get a little bit broader fuller understanding of what you see and the math to explain what you see. I would even say that once you get a master's degree in physics, you broadened it, and now you know all the big ideas. But in all of these big ideas, there's farther that I can go. The papers people have written, books that people have written that explain that concept deeper than what you would know in a graduate class. So kudos to you two guys that are asking all the right questions about implications about these lower level ideas, because the implications are very, they're far reaching, and maybe we'll dig into something specific here in a minute.
Yeah, for sure. And thank you. It is interesting. Me and Tyler, we grew up in a very small high school as well, and we would, after all our lessons, we would be sitting there talking about this kind of stuff and trying to figure this out. So when we had the same experience, we go to college and it's like a punch in the face. You're like, oh my gosh, this is
actually
so...
know nothing.
I don't know anything.
It's a healthy place to be, guys. Don't ever leave that mentality.
Well, coming out of high school, we thought we were like hot stuff because, you know,
Right.
we knew everything. Everyone was dumb. It was very humbling.
Yeah. I will say that jump, though, high school to undergraduate physics was probably the highest jump. The jump between, because it was a small school, because the level of things taught wasn't necessarily what's happening at a big school. You're taking AP everything, you know?
Right.
And that jump from small school Texas to university was a bigger jump really than university to graduate school.
That makes sense.
More prepared. I have a question about, so in undergraduate mathematics, the upper level classes, they call them proof classes. You start to prove a lot of the theorems or some of the stuff in mathematics, and I'll be taking my first proof-based class next semester, analysis. And yes, and this semester I'm taking intro to abstract, and it's kind of introductory to proofwriting and logic and that sorts. And I'm finding out that physics and all the courses I've taken in physics haven't really prepared me for proofwriting. It feels like a completely different skill that you have to learn. And what are your thoughts on that? Do you think learning how to proofwrite ever helped you learn maybe some of the harder theorems in physics, or deriving certain equations in physics? Does proofwriting help with that, or do you think that's separate?
Not separate. Help, yes. In math, in physics, there is various levels of if this, then this, and then if this, then this, and if this, and this. Now, physicists are a lot looser in this regard.
Right.
No,
mathematicians are always complaining about that. Yeah.
Whereas a mathematician says, if this, then this, but then you have another kind of implication. If this, then if and only if this happens, if and only if this happens, or if this happens, then this, but also if this happens, then not this and not this. Okay. And so there's a lot more branching, a lot more being precise and covering all possibilities for the mathematician. Where the physicist, you're looking at, I observed this. So in order for that to happen, I've got these kind of possibilities. So in other words, if I have two particles, they attract. All right. So the mathematician could say some things, but the physicist says, well, they are either oppositely charged or they're magnetic dipoles where they're oriented like this or like this. So the north and south are oriented so that they attract. That's kind of our only possibilities. The mathematician would say, but their gravity, the mass of these two balls could be just that high. Or the mathematician could say, but the strong nuclear force.
Right.
So whereas the physicist says, no, they're too far apart. Why would you even consider that?
Right.
Because I can have that much mass that far apart if it's that small. Why would you even consider that? Well, it's a possibility.
It's there, right?
Okay.
Right.
But now, as far as proof goes, the logic of this means this, and if this means this, and this means this. I purposely said that 3 times, because in my experience, 3 if-then statements in any physical logic is the kind of a soft barrier before you have to write it down.
Mhm.
And in math proofs, if there is more than 2 or 3 if then thises, I would call it a tough proof. And most of the proofs in these are 3, 4, sometimes even 5 if this then this that you have to get right.
Right.
It's 5 if then this that you have to learn individual packages that you
Mhm.
throw them all together. Usually in physics, we can get by with less.
Right.
So in that regard, physics is easier.
Yeah. Yeah, that definitely seems like it. So you said the leap from high school to undergraduate was bigger than graduate to or undergraduate to graduate.
Hey,
What? Yeah, okay, for you. What was graduate school like for you, and how does it differ from undergraduate?
so the chief thing, there's a lot of different kinds of stories, and I would call mine typical, and it wouldn't necessarily atypical, but undergraduate 15 hours a semester, and then you've got a smaller side job, call it 15 to 20 hours a week. Their work study, McDonald's, whatever, or a hobby, whatever you have. And then, of course, each of these classes take, call it an hour or two, maybe 5 hours per week outside. That gives you, I mean, that fills your time well. Graduate school, you're taking fewer classes. I took at most 2 main courses, and then always some sort of secondary auxiliary type grad class or research hours. So taking 2, and then of course my 10 to 15 hour side gig then became a 20 to 25 hour teaching assistantship or research assistantship, where, and as teaching assistantship, it's a real job. You're lecturing to students in physics, and so you're practicing things, but of course this is at a freshman and sophomore level physics, freshman and sophomore level, that you're teaching reciting or recitation, and then also in labs. So that takes quite a bit of time, but only 2 classes for the rest of your time, which means that those 2 classes, in order to master them, takes much more effort.
Do the classes so do the structure of the classes change from undergraduate to graduate, or does the material just get harder?
Yeah, it's the same. Okay. I don't know if there's a particular class you want to take an example of. You're in quantum?
I'm in quantum this semester, yes.
Okay, well, in graduate quantum, it's actually split into 2 semesters. The first semester is by and large covering what we teach here at Angelo State at an undergraduate level, covering the same thing with a few more details. Right. And so quantum 1 graduate school, quantum mechanics at Angelo State, they are for the most part comparable. There is another semester, of course, learning much more of the hydrogen atom details. And then not just hydrogen, but larger and larger molecules. How do quantum mechanics govern them? And how does angular momentums add together? A lot more detail about spin.
Right. We're just going to touch on spin. Yeah.
Touch on it in physics 1. But more problems for homework. But if you treat, and this is to me what helped me the most, I would say, if you treat every physics class like, I don't know this, and it's going to take effort for me to know this, and I'm going to, and I delight in knowing this.
Right.
As long as that's your mentality, it will serve you very well. So you're given a homework set. That homework set, wow, cumbersome. There's a lot of it and a lot of work. But then each of these questions, you get a result that hopefully is interesting. And so it's not a labor of pain, but a labor of love. I don't want to say trick yourself into it, but
right.
Fake it until you make it. No, I like that idea, especially with physics, where you have to build all these new intuitions. It's good not to go and not
thinking you know what's going on.
Yeah. Like you said before, you went in with like no expectations or anything. I imagine that's helpful when you have to build all these weird intuitions that most people don't have. It's cool.
And I think one neat idea next week, I know this is a dated topic, but Angelo State is going to host Alex Filipenko as a guest lecturer next Tuesday. And he has said in one of his podcasts that oftentimes he will be talking about a subject in physics that he is an expert in and be explaining it to someone. And while he's explaining it to someone, he realizes that he doesn't really understand as deep as he wants what he's actually talking about. That is me all the time.
Yeah.
And it's not because I don't understand necessarily what I'm saying. Like I understand it, but it's like, man, there's so much more that I want to know about this subject.
Right.
So I'm gonna have to go back to an old textbook.
Right. Exactly.
And absolutely in the classroom, I'll be teaching. It's like, man, I'm telling you this, and what I'm telling you is not a lie. This is really reality, but I wish I could give you more intuition. I wish I could tell you more about the implications.
Yeah. I give guitar lessons and I have a lot of these like guitar intuitions, and a lot of times when I'm teaching someone, I'll realize, oh, I don't actually know how to tell you how to do that. I mean, I can do it right here, look, but how do I tell you how to do that? I'm gonna have to go back to the drawing board.
I need Tyler to show you a lot is all the patterns, especially frequency and wavelength, these two. And then for the 1-3-5 chord, just a major chord, the ratio of the frequencies of each, and how do you create minor and major. And I'm sure they teach this to you, but how it's music is almost a large degree a mathematical pattern class. And so I mean, how do I get this sound? Well, it's this right here. But what your heart is telling me now is that I want to know why it's that sound. this string, and I pluck it here. I get this, but why? Why is there an overtone if I hold the middle and strum here?
Right.
Why is there a note here if I could go a third and do the same thing in it, and then I have another pitch?
Why does it sound different if I use a pick or a finger or a bow or
And again, you can try this if you have your phone. You can download the physics toolbox or a spectroscope, not spectra in light, but spectra in sound, and do the same note, but pluck it towards one of the nodes. And by plucking it there, Tyler he saw this last semester in mathematics about what resonances are created in the string.
Right.
And so by plucking it at one point and then letting it go, you're exciting more nodes. And so you get this high-pitched and low-pitched resonances on the string. Whereas if I pluck it in the middle and pluck it, it's a pure, you're primarily exciting the fundamental harmonic, like monotone, it's a pure single note sound. It's not quite pure because your initial conditions is a triangle. Whereas when the string vibrates, it's really a wave. So it's not purest form, but it's
pretty close.
And you can do with a single finger plucking the string. But that is explainable with physics, and very well.
Yeah, those questions weren't easy. I remember.
we did an episode actually where we broke down the anatomy of sound, and we talked about just like the components of like pitch, intensity, and timbre, and we broke it out like with the spectrometer and a few different other.
Send that to me, Tyler.
I will.
But we also Tyler, remind me this. We realized we had been looking at the same chart for a long time, right? Because I was explaining the overtones and the overtones on a piano and like the system, and I showed him on a chart what it looked like, and he was like, "Wait a minute, I've seen this before."
Right.
What was?
If you look at the harmonics, I guess for the overtones is what you're talking about. It looks an awful lot like energy states of a particle in a box, right? Because that lowest energy has that like half sine wave, and then that's like your first harmonic, and then the next highest energy has that like double hump sine wave, and that looks a lot like your second harmonic.
No, it's exactly what it is. I mean, the solution to Schrodinger's equation is exactly the same as the solution to the wave equation.
Yeah, and seeing those kind of seeing those connections, those are those bazinga moments and stuff. They make physics, and it makes it a lot of fun. So we were talking a little bit about quantum earlier, and I want to, I guess, start talking about some philosophical questions in physics we have nowadays.
Yeah, to get a sense maybe of like where you're coming from as far as just like because there's the math, right? But then there's also how people interpret the math. So
Right.
we're really interested to hear what you think on a few of these sort of more metaphysical questions.
And so the first one would be, well, the I would call it the classical problem of quantum mechanics. What is a measurement? And why is it the measurement? While we have an equation, Schrodinger's equation, that tells us how a wave function, a particle evolves through time. Whenever we measure a particle, we never measure a wave function, though, right? It's like the wave function collapses, is what we're told. And what are your thoughts on that idea?
So you've titled this section Metaphysics. So we'll stay there as opposed to looking at the math first. And what I would say, as far as taking a measurement, is that there's this same idea in other sciences, especially biology, a little bit less in chemistry. And in biology, the logic goes that whatever you're assessing in biology, you affect. And so, and this is from the sailor all the way to mammalia, the large, a fish, a whale. Okay. Now, from the cellular level, in order to understand what's happening at the cell, you have to irradiate it with light. That's the only way you can see it with your eyes. Now you can limit it. You can use longer and longer wavelength, less and less energetic, but the less energetic you use. Now, this is kind of important. The less energetic wavelength light you use, which is longer wavelength, you lose precision of what you measure. It also means you're affecting the cell less by the light you use. So the more and more you measure the cell, or the more information you get from the light reflecting from the cell or going through the cell, whatever, you have to use higher and higher energy light that can do more and more affecting of the cell. Until you get to X-rays, then you can find out what's happening at the atomic level in the cell. But what are X-rays going to do to a cell? It's going to destroy it. It's going to break apart the DNA strands. But that's how you can tell what the DNA is. All right, so then everywhere in between, there's similar types of logic, but then you get to animals. And how well can you observe a deer without affecting the deer? So you can place a video camera and watch the deer, and this video camera can be passive, very quiet, and you can be transmitting information from what the video feed is of the deer. But nonetheless, you put a video camera, and a video camera is not shaped like anything else that this deer has seen before. And so now there's not this direct correlation, but absolutely you measure or observe a biological object. The effect of measuring it, or you affect the object by taking a measurement. So now, fast forward to physics. And now, hopefully it makes, to me, a little bit more sense to think of there's an electron in the wild. Say it's an electron in some little cage over there. You put it in a cage, but it's doing its own thing, right? You look at it. You've done something to the electron. The electron knows you've looked at it.
Right.
I mean, it's kind of metaphysical, but I'm kind of being serious. You look at it, and then it looks at you, and it says, "Oh, you're right there." At first, I didn't know where you were in the box. And if I get and then of course all the measurements we know about charge distribution, we have to build a Gaussian surface, a three-dimensional Gaussian surface, and then based on the flux through this Gaussian surface, we can tell what charge is inside. And so this box that I put the electrons in, it's it's wild. I haven't looked at it yet, and so but I can measure the flux through it, and I know there's an electron there. But then I go looking at, and I actually measure more information about what the flux is where along the surface, and that tells me more information about where it's at. And the electron is like, I'm being measured. And so really, now, so say I measure a little bit more flux through one surface than another, that means the electron is closer to that surface. And therefore you've changed the electron, right? You know more information what you knew at first. And so it's not even looking at it, it's pinpointed. You just get a little information, and that little information you get from the electron affects its wave function. its distribution,
Right.
its probability amplitude.
So it's like we can't really, it's hard to see the electron as it is by itself. Well, impossible in some sense, right? We have to interact with it to know about it.
No, the bigger metaphysics question there is this idea of action, or spooky action at a distance, that Einstein put it, or quantum entanglement of spin. So you make this couple electrons that occupy the same state, and then I separate them without messing with their quantum numbers, right? So if they're in the same state, the only way these two electrons can be in the exact same state is if one is spin up and one is spin down from the Pauli exclusion. And then what you do, you separate them. So but all I know is one is spin up and spin down. Don't know which one is which. And I just separate them. So I've got this box with one electron, this box and the other electron, and they know what each other is. And I can separate them by a farther distance. Now, this is something that we can actually do. It's a macroscopic distance, but they keep their coherence, meaning the spin of one doesn't flip. Okay. All right. So it's either this or this, 50-50, both, right? You separate them. And then what you do, you measure one and you measure the other, and you send these clocks off. So these two people measure these two spins at the same time. And the big theory about information being transferred is that nothing, including information, can travel faster than the speed of light. But I measure one box, and by taking that measurement, I immediately know something I didn't know, namely, what is the spin of this other electron?
Even if it's a million light years away.
But if I know something about this that was not ever known anywhere else in the cosmos.
Right.
Now, I can't transfer information from me to you, but I have information at my grasp.
Right. So do you think that the electrons, so whenever we measure it, we'll see one spin up and then the other spin down, right? Were the electrons already spin up and spin down?
No, they were like the electron in the box. I know you're in there, but I don't know what you are. So same with the electron in the box that we separate. We know they're in there, but we don't know which is one. And the argument is the electrons don't know either. But and now I'm personifying the electron.
Right.
Because how
else do you say it though?
Yeah. But at the same time, the electron knows what it is. Maybe that's the answer to the question. The electron is
but like where this is gonna sound weird, but like where does it know it? Like where in the electron is the stamp that says what
I'm spin up?
do you have any do you have any intuitions on it, or do you just kind of leave it as like that's what it is, and you think they're maybe connected somehow in a way we can't see? Or
to me, so a couple explanations are that there's multi-dimensions, and so this electron and this electron becomes a positron, goes backwards in space in another dimension. I'm not joking, like this isn't a possible explanation, is that this electron then goes backwards in time and is equivalent to this electron because it's the same electron. You can look up the who was it?
We went over this paper in Modern.
UT professor that theorized this, not Weinberg. Maybe it was Weinberg. He postulated that in the whole cosmos, there's only one electron.
Right. Right.
And who's to
and
say
then
that?
because
every electron moving forward in time is physically exactly the same as a proton moving backwards in time. So right now the thinking is that for every electron in the cosmos, there's also a positron, which is that same electron moving backwards in space. So the fabric of space-time, you take a snapshot of it, and so one electron is going forward through it, one positron is going negative through it, and so they're moving in this sheet of space-time, but the actual positron is going through, electron is going through, and a positron is coming back somewhere else, and being holes.
And the intersection of that path is where we see the electron.
This two-dimensional space-time, again, space-time, 4 dimensions. So it's a 4-dimensional sheet, 4-dimensional construct. But you go into it, then you go out, then you go into it and come out. And so these two electrons know each other because they are the same electron. Kind of parallel to that is multi-universe or parallel universe discussions. And that can, I guess, explain it, but I'm not so privy to all those arguments.
Right.
To me, once you separate them, their wave functions are still unknown. But once I take any measurement, though, it's going to be found that it can't be up or down. Every measurement I take of this electron afterwards is going to be that it's down, because it knows that it's down and the other one knows it's up.
Mm-hmm.
In other words, I do an experiment to figure out, okay, what is this electron doing? Well, they know each other. So it's as if I give you a sheet of paper. One sheet of paper says A, one sheet of paper says B. They're in a box. And then somehow we separate the box so that we don't know which one is A or B. And we take these boxes far apart and we open up the box. And this one says A. Well, what does the other box be? What is it?
Right. Has to be B.
Has to be B. So, but then the same idea applies. Like, nobody knows which is which.
Mm-hmm.
But the A piece of paper knows and the B piece of paper knows. Well, maybe the electrons are cognizant.
Right.
That to me is actually slightly more
plausible than there only being one electron.
Yeah, and even
Right.
the parallel universe argument.
Mhm.
It's
Yeah. Nice.
So
Well, one
currently,
second
the
before.
explanation that Einstein tried to get away with is that there's hidden quantum numbers that we don't have access to, but
Right.
that still describe the electron.
the hidden variables.
Hidden variables, yes. And so a hidden variable in the electron then defines that it's going to be spin up, spin down.
So another interesting question, and we alluded to this a little bit before. There are some people who view mathematics as being like this platonic thing that actually exists, and we sort of discover it as we explore the universe. And there are other people who think it's sort of a human tool we've invented to describe real phenomena. And where do your intuitions go on that?
Math, as you know it, has at its core symbols. All the Greek letters, all the alphanumeric, the 1 symbol, the 2 symbol, and how to combine 1 0 means 10, and you repeat, and all these things. And those are absolutely human constructed symbols. And the majority of math, because it's developed by English language, a lot of it has to do with English letters. Like, so D for derivative, and the integration symbol is a long skinny S. It looks like a symbol, but it stands for sum. You're summing over infinite number of infinitesimally small little pieces. And even the time symbol being an X, it could be, like I was saying, a star. It could be any type of symbol you like. The division symbol. So to divide, you draw a number in a numerator, then a big bar and something beneath. Well, that we interpret that as being divide. We could have it be upside down, and as long as we understood that the upside down means something else, it'd be equivalent. Matter of fact, in physics, how to develop the spin and explain the phenomenon of the spin, there's 2 working theories. And after a couple of years of investigating these 2 theories, it was shown that they are equivalent. They're equivalent. Even though totally different symbols, totally different equation, it's equivalent to another in the mathematical core of how you get from the observations to the mathematical descriptor. Matter of fact, it goes so deep that for quantum electrodynamics, which is a crown jewel of physics, this is the field of physics that has measured and theorized the value of the gyromagnetic ratio of the electron, G. It's really close to 2, so we call it G minus 2. There's an experiment to measure it with higher precision.
Oh, yeah.
We have 13 current significant figures in it. So if you take a measurement of your speed in your car, you say it's 47 miles an hour, 47.5 if you want to be really precise. Well, this value we've measured to 37.45, 1, 2, 3, blah, 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 13 digits. That much precision. And we also have a working theory. And not just one working theory. we have 3 independently verified ways and to explain quantum electrodynamics. So a photon and how it acts like a piece of like a particle. This piece of light acting like a particle. There's a theory, and there's 3 working theories, and the best working theory is actually developed by Richard Feynman, who, whenever you talk about quantum electrodynamics, we always use Richard Feynman's diagrams with squiggly lines and stars. But there's 3 other equivalent, and it wasn't for a couple of years later that they were shown to be equivalent, right? And that is because each of these 3 theories are written both maybe by different people, different language, but using, for the most part, the same symbols, the same math. But it was shown eventually these 3 theories were one and the same. So what am I getting at? Is math simply a human construct, or is math something there to be discovered? So the symbols and the way we see it and the way we communicate in it is absolutely human construction. But adding 2 terms together goes beyond symbols. It goes beyond 1s, 2s, 3s, 4s, because you 2 having some math background, you can use whatever base you want. Like 7 base, or like 9 base 8 is really 11, right? I mean, it's not to confuse you, but you can call whatever you want to a number system.
But the relationship with that number to others is, we don't invent that.
Combining
it's already there.
What we're calling adding is absolutely, I would call it transcendent. It is something objective, something, even addition is beautiful, right? You've got a group of things over here, a group is over things over here.
Here's what I found.
And no matter who you are, where you're from, you have a way to describe 2 groups. What are they together?
So
I've got 3 here, 2 here. We say that's 5. But someone else says, I got blah, blah, blah here. I got blah, blah, here, which means I got blah, 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 blah. And most likely, if they have phalanges, they're going to do this. It's beyond math.
Right.
You know, so taking that from addition to abelian group theory, there's separation.
It's cool that you mentioned the Feynman diagram, because that's actually our symbol. It's a Feynman diagram with quarter notes and a few other things on it.
Yeah.
Wow.
So anyone who's wondering what that looks like, just look at our logo. So the real question, though, so yeah, I take what you're saying with we can use whatever symbols we want and stuff, but so if we were, just to get clear what you believe, if there were no humans, no language, no thought, no practices, nothing in that semblance, no like conscious beings, so to speak, would there still be mathematical like objects and principles that existed?
Proof is absolutely not on me whenever I say yes. How could anyone say there's not? I'm not being facetious here.
No.
I'm kind of being serious. I'm not calling anyone idiots either, I hope. Like maybe you 2 believe the opposite, but
right.
No, I don't take that view, but I have met people who take the view that there are like these mathematical objects that exist in some other realm. It's not an uncommon view, actually.
Okay, well,
right. Where they exist separate to physical reality in some sense.
So I think this could be a byproduct of some parallel universe theory where everything is the same, except when 2 things combine, 2 and 3. I mean, again, now I'm thinking at its core, a fundamental level, if I have a group of 3 and a group of 2.
Yeah, we're not talking about the symbols. We're talking about the
actual a group of 3 and a group of 2, and I combine them, and I get something other than what I combined them as. That's I don't have any idea. Okay. Now, here's the other thing: is we can take a group of 3 and a group of 2 and combine them no less than probably 100 ways. I mean, and it's not just add, multiply, divide, subtract.
Right.
You could take 3 to a power. We could take 3 to 1 over this power. We can. You get the idea. So there's ways to combine these, and that's the interesting thing. probably another bajillion that we don't know about, how to combine this with this. But do those other bajillion ways exist without us naming them?
Right.
Or do they exist whenever we do it?
Huh?
Or do they exist whenever we actually have the thought, make the thing, and boom, now it's there?
I would say that is here you this is where you got to dig yourself out of going in a hole that's too kooky. So in other
Right.
words, in the middle of the forest, if a tree falls, can you hear it, or does it make a
Right.
sound? Like,
Right. Probably.
was
Well,
there-
I'd say-
Seems like it would.
yeah, but that's the kind of same.
Right.
No matter what you answer, I can tell you you're wrong, or I can tell you you're right.
Right.
Right, yeah. I mean, that's how metaphysics typically goes. You can't, there's no experiment we could do to prove that. But it's more of just to get an idea of how you're thinking.
But I can absolutely tell you, and I'm 100% of this thinking, that there is math to be discovered that's really there, even though we haven't called it something yet.
Gotcha. Okay.
So in other words, there is absolutely a physics. I believe fully that there is aspects of what we observe that we don't know how to explain them with anything that we know about. It's a matter of us learning a true governing equation that's already there. That's the beauty. And that's actually ought to be, to me, at the heart of every scientist. Like, there's something out there we don't know, and I want to know it.
Yeah.
Right. So sort of in the
I'm not going to make it up either. It's there.
Right.
It's the promise, right? Not the promise. Like, you're not promised anything like that. But I mean,
so with that in mind, I want to talk about experimental and theoretical physics, kind of distinguish the two, or just talk about them. And the idea that I want to kind of put forward here is that physics at its core is an experimental based science. We do experiments in the world, or we see how the world acts, and then we try and describe it using mathematics and such. However, mathematics is really well developed. As you were saying, it's a much older science than essentially any of the other ones. And current theoretical physics is, well, a lot of current physics is largely theoretical. I should say we have theories, and then we're waiting for experiments to come and confirm or deny the experiments. And the idea I want to talk about is, whenever you are at the point in your theory that hasn't been confirmed by experiment, what sort of strategies do you do to continue developing the theory further, or developing new theories without the experimental backing?
okay. Well, this is a challenge. And I can't say that for my most advanced science career, have been up against this. So in other words, push the envelope of fundamental physics theory and fundamental physics observation. My cutting edge knowledge base is on superconductivity and its application to superconducting magnets. So all the challenges in an engineering sense of how to make the strongest magnetic field using the best superconducting materials. That was my dissertation project. Now, at some core level, the physics is not that hard. It's electricity and magnetism. The challenges, the Lorentz force is very large, the material is very brittle, and we want to get as high magnetic field as possible. And the Lorentz force that wants to tear the superconductor apart depends on the current squared, which is the Lorentz force. And so how to combine material properties, electricity and magnetism, magnetic properties, and throw all those together to make as optimized product as possible. You get how that's a little bit different than theory experiment. Okay.
Right.
Now, the reason why mine was still satisfying a physics requirement is because superconducting magnets I was building were for high energy physics experiments, which enabled colliding particles at the highest energy possible. Because the higher magnetic field strength you can make magnets, well, the higher energies you can collide particles and have more information about those particles. So,
And you're talking about the Large Hadron Collider right there, right? Uh, I'd love to get into that. Tyler, do you want to start? How about we move into that? Because I really want to talk about the electromagnetism stuff. So why don't we start just by, I guess let's start by defining physics, maybe. Just a good place to start.
Right.
Um,
The way I see physics is essentially just a way of trying to describe how stuff moves, more or less. That seems to be at its core what it is to me. How would you say electricity and magnetism tie into that, Dr. Holik?
So moves, I think you're limiting yourself to a lot of physics that's not moving.
Okay.
At least. So pushing or pulling would also, because a big chunk of physics is, well, what is causing things to not change? But kind of moving it, like what causes change, but also what causes things to not change. So I would broaden it from just things, studying motion, because at some regards you're limiting yourself to first semester physics or physics 1, because
Right.
physics 2 is electricity and magnetism, which is something that a construct. Now here, okay, is electric fields, magnetic fields. That's a mathematical construct that help explain how particles interact. And it's very helpful. It is a very, very helpful tool to define an electric field, magnetic field. And we can take other tools and measure what that field is. But so if I take a particle and it creates field over here, and I put a box here, and I can, well, how much field is inside my box? Is there energy associated to the field? Yes. Can I measure it? Yes. But is it a construct? Yes. We could explain the push or pull of other particles by other means. It's just the most helpful tool. So, but the field itself, if the particle is stationary, is not changing. It's not moving. It's simply there in a potential. Okay, is there going to be a particle that comes near me?
Right.
Is I'm going to push or pull on it. You just wait. And then the whole theory describes, okay, if this particle is doing this, this is the motion that you're saying. Like physics describes the motion, but it also describes the potential for motion.
Right.
Or the potential for the lack thereof, which would be stability criterion, also physics.
Whenever we tend to talk about electricity, we always include magnetism and vice versa. Why is that? What is the relationship between electricity and magnetism?
Okay, now this is so electricity, and I'm both pretty old. Magnetism a little older because some rocks have magnetite in them, and they can interact with other magnetite, which the uniqueness there is that they can attract or repel. And then also what I can do is I can rotate it and it changes as well. So there's a polarity intrinsic to magnetism, which is important to observe without, anyway. Then call it 400 or 500 years ago, you could put two different metals into potatoes or lemons or anything with an acid, because the attraction of electrons to two different metals like copper or nickel are different. And so it pushes electrons away from one of the metals towards another. And then you can have we now know as a voltage. You can stick this voltage on the legs of some dead frogs. The dead frog's leg jumps. I'm serious. This is kind of how the first experiments were done with voltaic cells. And I mean, 400 or 500 years ago. And then going back farther, you have thousands of volts created with rubbing bones along the fur of the animal. You have static electricity, and so some goofball is probably with fur and rubbing a bone on it and then say, "Ha, a Shakti,"
right?
1,000 years ago as well. So the observations of the two, while separate, are quasi ancient. But then fast forward to, call it 1800, which was the first experiments done that noticed that it is currents that produce magnetic fields. Now we still have magnetic materials, and so we didn't know that it's actually currents inside the materials themselves, electrons moving or orbiting the nucleus that causes a current, that is the origin of the magnetic field from these two chunks of magnetite doing the attracting. But what gives rise to currents? Electric fields or voltages. So that was the first coupling between electric fields causing currents and the currents themselves creating magnetic fields. So that was like 1910 by, I'll be lying to you.
Well, it started with Maxwell, right? Or
well, this is 50 years prior to. So then, okay, we can fast forward there, but there's another key step along the way that currents create magnetic fields. But then also what you can say is that changing, so the currents create magnetic fields, that's a current moving. And if the current is being accelerated, it does more than that. It creates a changing magnetic field that then can create a changing electric field. And so the key little component that Maxwell added is that if I have a changing electric field, it causes a changing magnetic field. Faraday's law says if I have a changing magnetic field, namely, if you've seen experiments where you can drop magnets down copper tubes, or if you're on a roller coaster and you feel yourself braking, but there's no squeak like a brake pad ever touched something, well, that's because there's magnets on the side of either your roller coaster or on the rails, and you move a metal along that magnet and it drives eddy currents that oppose the change in flux and cause you to slow down. So that changing magnetic field causes an electric field, causes currents. That connection was known. The connection that Maxwell added was not that changing magnetic fields cause changing electric fields. He added that changing electric fields cause magnetic. Huge. This was 1860.
So they cause each other.
They cause each other. And moreover, it is the fields themselves doing the causing. So if that's true, if this one's changing and it causes this to change, which causes this to change, and so now they're both changing, and it ends out that they change together, but they change perpendicularly to each other. So it's like doing this. One is oscillating, this one's oscillating sideways.
Yeah.
They're doing this and propagating. And what was beautiful is that all the equations up to that point, we knew all the constants. So how does electric field affect space? How does magnetic field affect space? These two terms for electric field is called the permittivity of free space, or epsilon, and how magnets affect space is called the permittivity. So,
permeability.
Permittivity for electric field, permeability for magnetic. And these two constants alone are all that's necessary to describe how these fields oscillate from each other. And it turns out that the speed of this wave, mathematically, this is where mathematics was known 200 years prior to, because the equations governing waves was well thought up already. And solutions, what they look like, are already existing. And so he said, I know the solution to this equation. It's a wave. And the speed of this wave is 1 divided by, again, I'm going to use my hands and these symbols, constructs, right? 1 divided by the square root of these two constants, mu and epsilon. And 1 divided by the square root of these two constants ended up being 3 times 10 to the 8th. And it's a speed, so it's meters per second. And to know what is that representing?
Only light goes that fast.
So what he had no idea what he's doing. He saw the symmetry in the math equations. He added this slight term, and then boom, the speed of light came out. He said, "What?"
that is
right.
weird.
Working theory at 1860 was Newton's argument was that light acts like particles.
Right. Corpuscles.
Pusculars of light thrown from the light source. I have a hot body, and it just missed little pieces of light. And it wasn't dumb. It was like if something is going to go through space and it doesn't need anything to go through it. And this is why he called it a particle, right? Because I've got a vacuum, I've got nothing there. And if it was a wave, well, something would need to oscillate. It would need an ether. This is the name they gave this magical fluid for light to go through, because they said, well, if it's a wave, which kind of acts like a wave,
Yeah.
we can diffract it, we can refract it. This stuff is a wave. And the same time, Maxwell's the one that said, no, look at this. I just combine electric fields and it's the speed of this stuff. This is it.
All right.
This light that you're observing, it's electric fields and it's magnetic fields. See, look, the math proves it.
That's very interesting.
And so this is why electromagnetism is inseparable. And I'll do you one better. There's another, perhaps even stronger argument. Because the thing that cannot change whenever I go from one frame to another, it's Lorentz invariance. This is important physics term. So if I go from one reference frame to another, there are certain things that cannot change, namely the energy of the system. So if a box and it has a certain energy and I go to a moving reference frame, well, the energy in that box better stay the same. That means that energy is what's called Lorentz invariant. Well, electric fields by themselves are not Lorentz invariant, but electromagnetic fields together are. Now, here's why I say that, because if I put a charge in a box and I'm in the reference frame of the particle, it emits electric field all directions away, okay? But if I start to move, what does it look like that particle is doing?
Well, looks like you're in a changing electric field at that point.
I'm in a changing electric field, but then it looks like this electron is moving. And a moving charge creates
Current.
or current, and currents produce
Magnetic fields.
magnetic fields. So depending on my reference frame, either I'm in a pure electric field, but if I'm in a frame of reference moving that direction at the speed of light, I no longer have an electric field. It's purely magnetic. So electric field by itself is not Lorentz invariant. Magnetic field by itself is not Lorentz invariant, but electric and magnetic field combined is Lorentz invariant. That's why it's strongly coupled. And that's probably the strongest argument why they're coupled, not just light. Like that's a really pleasant, cool side effect. Not a side effect, like it's
Well, I was gonna say that's incredibly interesting. And how does it play in with relativity? Because you're talking about the frame of references. It sounds like you're talking literally adjacently to relativity. So
I am.
What's going on? How does that work? Or
Electric and magnetic fields are intrinsically Lorentz. By being Lorentz invariant means that they obey special relativity. So in other words, going from one frame of reference of another, considering the electric and magnetic fields and the total energy and the momentum and the angular momentum, they don't change. They are conserved quantities, which means that because they're Lorentz invariant, it's at least as far as special relativity and relativity are concerned, they are the deepest understanding we can have. So it doesn't, in other words, going from one frame to another, it doesn't matter. It stays the same for all reference frames.
Right. So you pointed out earlier that we have these two numbers, the permittivity and permeability of free space, and they're just two constants.
Yeah.
And if we do 1 over the square root of them, no matter what reference frame you're in, those are just two constants, right? And so you're always going to see the permeability and permittivity as those constants, and that those constants are telling you the speed of light. So essentially, no matter what frame you're in, you're just going to see the speed of light as 1 divided by the square root of those two constants, right?
Now, like these constants change from one material to another, but it absolutely does not depend. But I mean, light going through gas or light going through glass or water slows down. How much does it slow down? By exactly what those constants are.
Right, exactly. We usually say mu naught and epsilon naught for vacuum, right?
Right. So, and again, because those are constants based on the material, it doesn't depend on the reference frame. That's the beauty of a thing being Lorentz.
It's like an intrinsic thing.
Matter your frame of reference. Which the implications of that. So, in other words, special relativity and even general relativity were founded upon this constancy of light. So Maxwell showed light acts like a wave. That was the basis of special relativity. Like it wasn't like special relativity was a separated idea. Maxwell's equations and the wave equation of light is the basis of special relativity. So it's not like it obeys it. It is the cause or the core of special relativity.
That was really cool. Nice. Okay. Well, so to move on from, well, not move on, but to build upon that, you talked about your work with the LHC, which is an amazing piece of equipment. I was reading over some of the work you had done on it, and I was reading about the LHC, and I don't know much about electromagnetism, but why does the LHC need so many different kinds of magnets? Like, what is it actually happening there? Like,
a great question.
Yeah.
So the Large Hadron Collider is a ring, a circle. And so in order to make these charged protons move in a circle, you need dipole magnets, meaning the magnetic field is only pointed in one direction and it's uniform throughout. Dipoling meaning it's pointed in over here and coming from over here. It's dipole, single direction. That's what actually causes the particles to move in a ring. Okay. Now, of course, particles, they're all protons. What do they want to do? They want to push each other away. So depending on how fast they're going, if they're going really fast, then they don't push each other away as fast. But if they're going slow, well, then they push each other away slower. Excuse me, if they're moving slow, they push each other away fast. Nonetheless, this bunch of protons, they diverge, they can separate. So what you have to do is focus in, cause these protons moving in a ring to keep them from diverging. You got to squeeze them. And you can do that with a lot of different magnets. You can do it with a solenoid field. You can do it with a quadrupole. You can do it with an octopole. And actually, all of them are needed to fix errors in the dipole field of the magnets that cause it to move in a ring. The most important of these, though, are the magnets just directly in front of and behind the interaction region. So that's where the magic happens whenever we cause these two beams to cross and collide with each other. So the magnets just on either side have to be uber precise in order to squeeze that beam to as small as we can get it, and then have them, so it's less than the size of a pencil lead. Right now, it's about the size of a pencil lead. The magnets that I helped develop a couple of years back are going to attempt to make it from pencil lead to something closer to a couple diameters of your hair.
Oh, wow.
And then have them perfectly hit each other. And we can tune in the magnets that I've helped develop. You can place they have to be placed specifically where they need to be. And if the electric and magnetic fields inside have to be very, very precise. And that was my work, helping develop these magnets to make a very precise magnetic field, magnetic quadrupole field. So the magnetic field in one direction is towards, and in the other direction it's away from. So it actually focuses the beam in one direction and defocuses it in the other, but we have two of these together. So one quadrupole and then one quadrupole that's rotated. So the net effect of this squeezing in one direction and pushing away, the net effect of both of them is that they both squeeze once they get to the actual interaction point. This is why you need that many magnets, because some are bending the magnet, or bending the particles. Some are focusing the particles. That's the two functions. But in order to focus them, you need a bunch of different corrector magnets.
Well, there really is so much I could talk about and listen to you talk about this, but I guess at some point I'm just gonna have to go take a E&M class at ASU, because you have a lot of really interesting stuff to tell. But we can go ahead and try to get wrapped up. So I think one thing we like asking people like yourself who've done lots of really interesting research and work and gotten their doctorate and stuff, I imagine you worked on tons of different projects, and we've talked about some of them here. What would you say is the most and you can do this in either order, but what's the most difficult project you've ever been a part of that like challenged you the most? And then also, what's your favorite project that you've worked on?
All right. Difficult. So there's a lot of levels of difficult. Like one is simply to understand. It's difficult to understand. One is difficult to fabricate. One is difficult to politically have happened. And politically means getting people on board to support. And so each of those realms, I'd have a different answer. And so to build, man, like, so my dissertation project was a magnet. It was really tough to build the entire thing. But the issue, so it's one of the same with the most difficult politically, because my dissertation project was building a superconducting magnet, and it was built at a university to the tune of about $750,000 per year for 5 years.
Wow.
Which is $3 million, $3.5 million, which is a lot of money to spend kind of on a single graduate student. So most likely, and nobody's done it since, but mine was the last dissertation in America that was in superconducting magnets, where a magnet was actually built at a university. Now, other people have gotten dissertations in high energy physics, of course, but none building a magnet. I'm it. And the reason is because of expense. It's much more cost effective to have a national lab develop the magnets, and that's what I did for my postdoc. So that's that, and so in some regards, politically, and most difficult. So ultimately, my dissertation project was a failure. We said that we were going to obtain about 13 Tesla or 14 Tesla dipole field, and we obtained 8.
It's still a lot.
Yeah, I mean, that's
8 Tesla is
huge,
heavy,
but
1 Tesla is a lot.
But
of
in
magnetic
terms of the
field.
force,
Right.
remember it's current squared, so 8 squared versus 14 squared
Oh, I see.
is what the force would be. So it means that it should have been able to handle a lot more force, but it didn't. The conductor broke apart, and there's a lot more reasons why, but and because it was such an expensive, and my hands were on a lot of it, but it wasn't just me. Like, I only built small components to it. There was a whole team of full-time machinists, and had to go to California for the conductor, had to go to Berkeley to have it tested, and other national labs in order to have so much of it done. So honestly, if it would have worked, it would have been an amazing combination of all these things together.
Right.
So it just wasn't as successful as possible. But I would say the most difficult conceptually was my master's project, which I would have loved to have finished, but it was in plasma physics, and in plasma physics is really difficult, really, for 2 reasons. One, you have to understand things statistically. And Tyler, you'll have to take statistical mechanics or dynamics at some point, but understanding things statistically is a challenge. And then to the first approximation, what you assume whenever you're dealing with a lot of particles, that they don't interact. But a plasma, you have a bunch of particles, a bunch of atoms moving around, but it's not just atoms. The energy is so high in a plasma, so that by definition, the electrons and the positive ions or nuclei are separated from each other. So for hydrogen, the ground state potential of an electron is 13.6 electron volts, which that, if I convert that to a temperature, is like 100,000 Kelvin. Hydrogen plasma would be 100,000 plus Kelvin. But if you use something more stable like argon or neon or something, where you can get by with 7,000 or 8,000 degrees of Kelvin. But nonetheless, the difficulty is, if I have a positive ion and an electron, they attract to each other, and they want to become in a bound state.
Mm-hmm.
So the physics governing plasma physics is very involved. And I wrote equations that would solve it, but intrinsically, you have to simulate a lot of particles, or treat the particles as a fluid. And so there's other regimes where you can solve the problem. And so I did that as my master's thesis, and made plans to build a plasma torch, a plasma gun, that would be very much unlike what anyone else has done. So the idea that's nice about a plasma is if you can have the plasma driver uniform and introduce gas through the plasma, what you can happen is gas that goes through the middle and it gets very, very hot because the middle of the plasma will be the most energetic. And then towards the outside, it's very cool. So cool so that I could feasibly touch the side of the containment vessel and it not burn you. So I can introduce gas out there that would not get hot. Nobody's taken advantage of this, even to this day, that I can introduce gas into a plasma in the hot region and introduce gas in the outside region that's not hot and do something with that. So the idea I'd like to think is if I put butter and a chunk of titanium into this plasma torch, where I put the butter on the outside cool region, I put the titanium in the inside cool region, I can actually coat, by introducing turbulence on the backside, the butter with titanium. And I'm being serious. You tell me any way possible that I could feasibly coat butter with titanium on a microscopic scale, a micron size particle scale. Now, this is for fun idea, but you could do it with a lot of other interesting things. So you can plasma coat soft materials with a harder, high melting point material that nobody has done before. You can also, by having one material be cold and one material be hot, have them mixed in the end, so as a precursor to other materials. And the whole motive for this was that I can make amorphous, a boron precursor to make magnesium diboride superconductor, which the more amorphous, meaning the more uniform you can make the boron, the better superconducting properties you can have magnesium diboride, which is a superconductor. And it has also really unique properties by itself, magnesium diboride. And ran out of money.
Right.
So I could have at this point made a choice. And if I was to advise myself, 12 years ago, I would have told myself, write a grant and get money and make this your dissertation PhD project. Because again, it would have been not world changing, but it would have been something absolutely new and interesting. And not that my magnet wasn't new and interesting that I built for my dissertation, but
it's a different kind of new. I mean, an improved magnet cross section is one thing, but like you're talking about an entirely
a new field of material science.
Right? Yeah, that's incredible. Yeah, surely people would grant that. They'd be crazy not to. That's just, I don't know. If I were rich, I would grant it. I would make a grant for that.
Who doesn't want to coat butter with titanium?
Right, exactly.
I had those a long time.
So those were the hard ones. Were any of those? Did you prefer one over the other? Do you have a favorite project you've worked on?
Now here's where I think this is a great question to kind of conclude things on, because physics is a very satisfying field to me. I like all of it. Right now on my desk, I have, because I've taken a particle physics book or class in graduate school, but I didn't have a very good, the teacher wasn't very good, so I didn't learn nearly as much as I would have liked. But I got a elementary particle physics textbook that I'm reading through now. And that is exciting to me.
Right.
And so you run the gamut from elementary freshman 1 physics to rotating on a frictionless table and that gripping me and just saying, this is what I want to know more about, to now 20 years later, on my 20th physics, that I want to understand better particle physics. And so your question is do I prefer one over the other? The question is, well, yes. But now you ask which one? All of them. Physics is, and now I can tell you a little bit more about me personally. And so I am a Christian. I believe in the Bible, which God created everything we see. That is my baseline, my worldview, if you will. And so whenever I look out my window, I see a blue sky. I see white clouds. And I see a distinct, and that's literally what I see right now.
Yeah.
And a distinct break or line between the cloud and the sky. And it's very pretty, first off, which is awe-inspiring enough to the non-physicist. But the physicist sees that as there's moist, warm air rising and cooling and condensing. And there's a breaking point between the water particles being too small to diffract light, then breaking a barrier in size so that no longer do you have transparent water vapor, but you have Y scattering, W-I-E scattering, which is, or excuse me, M-I-E scattering, which is why clouds appear white and why they're so distinct and sharp-edged, because at that edge, the water droplets are large enough to diffract light. Now the blue sky is because of WE scattering, W-I-E, which is another realm of the dust particles being small, and they preferentially, by the way, me scattering, it doesn't care the wavelength. It scatters everything the same. That's why clouds are white. But me scattering, which is for, I always get these, whatever, for the blue sky, is a wavelength or frequency dependent scattering whenever the particulates are small. So that means that the high energy wavelength light is preferentially scattered first, and the longer wavelength red light is scattered second. And so this is why you look at the sky and the preferentially blue scattered light is reflected sideways from the sun. So if you look at the horizon, well, all that blue light is already scattered out. And what you see is red and orange. So again, it's beautiful, but the physicist sees more of the beauty. A physicist looks at the night sky and sees stars and has an inkling of how far they are away, how bright they are, their energy, the massive power of the gravitational force field, the potential of planets orbiting these outer bodies, the age of light, or apparent age of light coming that we're detecting and are about to detect in 2 months and be shown in 2 months. The James Webb Telescope. I've got 2 months thinking about it, guys. I'm really thinking about the amazing things that we see. And so from my worldview, my motive is to see the fingerprint of God, the creator. And the fact that so much of what we see is tangible and governed by seemingly simple equations, like L equals R cross omega. All I got to do is say that, and that explains 100% of my first magical angular momentum on the frictionless rotating Susan. And even now at the end of a class I'm teaching this semester, statistical mechanics, the statistics governing electrons, fermions, and the fact that the Pauli exclusion principle prohibits 2 electrons occupying the same state, that principle that is quantum mechanical in nature governs stellar evolution. So how a star becomes a supernova, how it dies into a white dwarf or a neutron star or a black hole, those 3 deaths of a star are all governed by statistical mechanics. And the equation governing it, come to my lecture tomorrow. But I can write it on a chunk of the chalkboard this big. And the size of a star that's going to become a black hole or going to become a supernova, I can write on a chalkboard with this much of our known mathematical symbolism. If that doesn't cause you to go, wow, at least, or if not, have your mind blown that we can grasp something that complicated.
Yeah, we can actually know something about it.
I was saying to someone earlier that even momentum, like maybe everybody has this idea that if I have a big rock and a little rock and they collide, well, the big rock is going to cause the smaller rock to move forward. I knew this coming into graduate school, or not graduate school, but in physics. But physics says momentum is conserved, which is something very simple, that the mass of one times the velocity of it is in the mass of another times the mass of that object, and they collide. That's conservative. And so P equals mv describes every collision. The collision of a proton with a neutron, the collision of a car with a tree, the collision of a star with a planet. P equals mv. If that doesn't cause you to say, okay, or wow, or oh, that's beautiful, then you ought to rethink about what.
Right.
Don't
So
become a physicist.
It's I mean, the other thing is physicist, if you teach it, I have the double delight, and I get to teach myself and teach others this beautiful subject. The thing is I don't actually have a deliverable. So in other words, I'm not designing an object that something can make someone money.
Right.
I students money by helping them understand things.
Right.
I don't make money.
Yeah.
Right.
But you get to give that spark that you got to other people, and that's a beautiful thing.
And it is very satisfying. Yeah.
Well, thank you so much. I know you need to get going. We really appreciate the time you've given us and
Pleasure was
talking with
mine.
us.
If y'all have a follow-up question or discussion thing you want to talk about, let me know.
Oh, yeah, for
There's
sure.
other faculty that probably would.
I was thinking about going to other departments, maybe asking a biology professor, a psychology professor, or something like that.
Absolutely.
Right.
Absolutely.
I'm sure I'm sure I could find someone that would like to come on, right?
Yeah, I saw it.
We have great professors
here. Names, if you want.
Okay. Yeah.
Well, thank you guys thank you those who listen. If you have any questions, feel free to leave them in the comments. And thank you again, Dr. Holik. Appreciate you.
Yeah, the pleasure is mine.
Until next time.